Alright guys and gals, we've got a pretty quick video tonight. Basically I want to go over the Chapter 9 equations. We'll start working some problems the next couple of days, but I want to at least get you the equations so when you start your web assign, you've at least seen the equations, you can start plugging some numbers in, you can start figuring out what's going on just by knowing what we have here. Alright, so the first equation we're going to look at is our impulse equation. And our impulse is what we tend to refer to as fat math. So it's force times our change in time equals our mass times our change in velocity. So what we do there is we are now applying a force through a time, and as we do that we should be able to measure how that affects a particular mass by changing its velocity. It comes in pretty handy. We'll see it like when we're hitting things like a golf ball. How long is that golf ball in contact with the head of the golf club? Tennis racket, tennis team, Team Sigwing, Team Weiss, ladies, The View, Nichols, McDaniel, you gals. When a tennis racket hits, boom, if it's in contact longer, it's going to affect the force and what's going on. Alright, well, next equation we have P equals mv. This is kind of what I refer to again as one of our freshman equations. This is one of those things that we've seen for quite a while. Even though we haven't seen it for a while, it's something that we should know. That's momentum. So remember, momentum is referred to as P. So P equals mv. Mass definitely affects the momentum of an object. If you have a larger object, like you have John running into somebody at a high velocity, compared to, let's say, Kendra. If Kendra runs into somebody at the same velocity, different momentums, so we're going to see that affecting people differently. Alright, the next equation is going to be the impulse that we started with, the fat, the force times our change in time, equals P2 minus P1. Now, here's why we write it this way too. Is sometimes we end up with a mass that doesn't change. Okay, all we're worried about is the momentum. So when we look at that top equation, that's all that is. It's going to be mass times delta V, which is the second equation, momentum. I've got it right there. Okay, so momentum, which we have in the top equation, is momentum down here as well, because we have a change in velocity, but the mass is going to remain constant, so we're still good there. We can use this in place of the math portion of our impulse equation. So same stuff, just written a little bit differently depending on what information you have. Alright, now the bottom one. The bottom one is just showing us that the momentums, if we have two objects that collide, when they collide, our product is going to end up being the same as what our initial momentums were. Our momentum is going to be conserved. So we're going to conserve momentum. Now again, this is a perfect world situation. We're not going to deal with friction and all that jazz. So even in that case, it would be conserved, but we wouldn't be able to record it, at least with what we're doing. So the momentum what we start with is going to equal the momentum with what we end. So when we are working out problems and we see momentum, it goes from one place, it's going to end up on the other side as well, which will help you out considerably. Alright, if you watch this tonight, congrats, you've done good. No free prize tonight. But tomorrow, I will shake your hand and tell you, good job. Alright, so have a great evening. We will see you tomorrow.